Hey everyone, we're excited to share with you embeddings for measuring text relatedness, unveiling sentiments and relationships in online comments.
Okay, so before we start off, we just want to give you guys a brief overview of what we're doing and how we started off thinking about this project. So initially, what we're doing is using embedding models to turn an input text into a vector representation. So basically taking input, tokenizing it, pre-processing it, and cleaning it, and then turning it into a number representation for the computer to interact with. And this can help us find semantic similarities and other trends as well. So we're not finding just sentiment analysis, we're also using more trends to find interconnected patterns with the internet. And this provides insight to whether the internet operates as an interconnected brain. So as you see in this graphic, we have a basic pipeline of what our process looks like at the start. We have a small data set compiled from 3 different platforms from the new Mission Impossible movie. And essentially what we do is pre-process and tokenize the text, feed it into an embedding model, and finally find trends that we're looking for.
So this is just to give a little bit of context for our project. In the past few years, sentiment analysis and natural language processing has risen in popularity and taken many uses. Previous works have explored context-aware models and methods like CCA. These methods have allowed businesses and individuals to gauge public perception and adjust strategies accordingly. Now, for a standard sentiment analysis pipeline, it would begin with choosing a model and then text tokenization, which works by breaking input text into smaller units like words, and then data normalization by converting the text into numbers and then using these numbers for sentiment classification.
Some challenges that our area of research currently face are that many of the approaches to sentiment analysis are very computationally expensive, requiring high RAM usage and taking hours to run. Additionally, for this project, we wanted to ensure that we were using effective embedding models that were aware of context surrounding each word or sentence, as context is a big part of social media posts. A lot of the text that we got from Kaggle datasets were unstructured and had lots of variations, especially across datasets, meaning that we had to do a lot of cleaning on these datasets. Finally, we came up with a novel approach to text analysis in that we were tracking underlying trends across multiple social media platforms, such as Twitter, Reddit, and Amazon reviews. So we had to come up with a new approach to effectively analyze. So the 4 main goals of this project was to first explore the shared sentiment in social media comments across multiple platforms, which sets us apart from previous studies. The platforms that we chose were YouTube, Twitter, Reddit, and Amazon. Additionally, we wanted to use multiple NLP techniques to analyze the relatedness of embeddings, most notably cosine similarity and other metrics. We also used clustering to find the magnitude of shared sentiment to further our investigation of the internet as an interconnected brain. Finally, we investigated KL divergence to analyze social media posts over time and determine trends in sentiment.
Okay, so the first step we had to do was embed text. And for this, we researched and experimented with multiple NLP models. And then we used many, but probably the most important ones to take away is BERT and Instructor XL. And to test the usefulness of such models, we use measurements and methods, things like cosine similarity, which is used to determine text relatedness, KL divergence to determine how opinions can change over time, and k-means clustering to determine the sentiments and how opinions can cluster together, and silhouette score, which is part of clustering to determine the quality of clusters. And now the graphic kind of shows the methods and kind of the steps we took. First thing was to collect data, and if the data wasn't clean, we have to clean it. And then we have to embed the text using our NLP models and then measure the relationship and trends using measurements and methods that I previously discussed.
Many factors played into how we decided to use which embedding model to use. We needed a model that was memory efficient given our large data size, but could also run quickly. However, we also needed a model that created high quality embeddings. For example, Instructor XL was highly efficient as a model, but created low detailed embeddings. Lastly, we needed a convenient model. Some models were pre-trained, which required no hyperparameter tuning, and others were very user-friendly to implement. Sentiment analysis is a natural language processing technique that involves determining the emotional tone or sentiment expressed in a piece of text, in our case, social media comments. In our testing, we utilized multiple datasets constructed from YouTube, Twitter, Reddit, and Amazon. Combined, we tested over 2 million comments. After running sentiment analysis, we noticed that some models created poor quality embeddings, while others struggled with correctly classifying each comment. The first graphic displays what a sentiment analysis would look like on a text, and the bottom graphic gives an example.
Okay, so the first main experiments we ran after sentiment analysis and basic semantic measurements was clustering. And we divided it into 5 main steps to help you guys visualize what we did. So the first step was finding the right data set. Initially, we used a Reddit comments data set, but then we moved on to a mixed data set, as Justin said, using over 2 million comments. The second step was using the embedded data set on models like InstructorXL, Albert, and Siebert. The third step was to use the elbow method to optimize the number of clusters. As you can see on the graphic to the right, the elbow method is a heuristic graphic that helps us visualize the optimal number of clusters without any manual hyperparameter tuning, which can be quite tedious. So in the graph, you see the elbow method or shape that forms an elbow is at 4. That was the optimal number of clusters we chose. Step 4 was to use k-means to create the clusters for the dataset. And as you can see to the second graphic, there is a cluster assignment for the XLM Roberta model, the Roberta checkpoint. But step 5 was to test the cluster quality using the silhouette score. As you can see, the clusters are ill-defined and subpar because they're not well separated. A silhouette score of close to +1 means very well separated clusters. A silhouette score of close to 0 means overlapping clusters, and a silhouette score to -1 means items are in the wrong cluster. So the XLM Roberta model achieved a score of around 0.2.
Another important measurement that we used was scale divergence, which we also broke into 5 steps. The first was to choose a specific time period to look for divergence of opinions. The second was to embed the text with our models. The third step would then be to average each vector of the embeddings to gain a single representation. The fourth step was to create probability distributions with the data over each time period. And the last step was to calculate the divergence between the 2 distributions. And by doing so, we'd end up with a score ranging from 0 to 1. If it's close to 0, that means that the opinions over the time periods or the sentiment over these periods didn't really change. If it's closer to 1, that means there's a higher change in sentiment over time.
Upon testing of various embedding models, it becomes evident that the Roberta checkpoint models are the most promising performers in terms of overall effectiveness. In contrast, the InstructorXL model exhibited the least favorable outcomes among the evaluated options. However, all of the Roberta models, as well as the Albert model, truncated text exceeding 512 characters in length. Intriguingly, a mere 0.5% of the complete dataset contained instances of text that surpassed this 512 character threshold, meaning that truncation of data points over 512 characters had a relatively negligible impact on information loss while embedding. We used these results to determine which model we will use for divergence analysis.
Of all the models that we tested, Siebert performed the best in the metrics we used to identify online trends, using a dataset of comments from multiple social media platforms. We got a sentiment analysis score of 99.13%, which meant that the model classified the sentiment of text data very precisely. We got a silhouette score of 0.81, meaning that the data points were well separated into clusters, which you can see from the distinct color groupings in the clustering visualization. This means that the sentiment over the dataset were equally balanced, but within each cluster, there was strong similarity. Siebert was also easy to set up using the sentence transformers library, which allowed for less code. Overall, Siebert gave us the best quality embeddings and the best results. In order to analyze trends in our data, we applied weighted averages to our datasets to gauge what the overall opinion on each platform was, a negative score indicating a more negative opinion and a positive score indicating a more positive opinion. In order to find out whether opinions changed over time, we performed KL divergence on an Amazon dataset with 500,000 plus reviews. We used Siebert to analyze opinions from 2 different 4-year time periods, and we got a divergence of 0.87, meaning that there were notable differences in the sentiment expressed about the Amazon products between the 2 time periods, and that public opinion did not stay consistent over time. Once we saw that Siebert worked well in classifying the text embeddings, we decided to do further data analysis for purposes like calculating general sentiment. By using a Twitter dataset of 100,000 tweets about the Prime Minister of India, we found that the public opinion of him was slightly negative, yielding a value of negative 0.2 using weighted averaging.
In our conclusion, we explore the use of word embeddings, analyzing online comments to evaluate trends across social media platforms. Fast text, as can be seen on the graphic, fast text achieved a modest accuracy of 62.89% in sentiment analysis, while Instructor Excel obtained a silhouette score of 0.062, indicating suboptimal sentiment classification and clustering. However, robotic-based models showed the most promising results, and Cyber was the most effective and optimal in sentiment analysis. So using the KL divergence and our other results, we concluded that internet isn't as interconnected as we initially assumed, and opinions can be volatile as they change over time. The internet appears to be split over the same topic very fairly, but those who have the same opinion are very strongly correlated.
In the future, we could extend the study across various languages and examine sentiment analysis across global regions. Also, expanding to other social media platforms provides a wider internet perspective. Gathering data from demographic-specific platforms reveals holistic insights exposing subtle patterns. This could involve region-exclusive, youth-centric, or business platforms. Moreover, the investigation into sentiment analysis within specific industries will persist with applications in marketing and politics. These efforts will enhance the real-world relevance of sentiment analysis.
Okay, before we wrap up the presentation, we'd like to thank all who have assisted us throughout the research process, especially the last of our research program. We'd like to offer our gratitude to the researchers whose previous work has been inspiration and acted as a foundation for the study, especially authors of the Kaggle datasets. And we know Arjun and Nishk are not in the acknowledgements or the authorship, but we'd also like to thank them for their immense support throughout the program.